The ground was only warmed by 2.3 degrees Celsius, but in one small plot of Arctic tundra in Alaska, that was enough to disturb carbon that had stayed locked underground for thousands of years. The plants on the surface grew thicker, greener, healthier, and still, the soil beneath them began losing the climate battle. That is the part that unsettled researchers, because this patch was supposed to follow the rules: warmer air, more plant growth, more carbon pulled from the atmosphere. Instead, the deeper story was happening below 40 centimeters, in frozen ground no one could see. So how does a greener Arctic become more dangerous at the exact moment it looks more alive? At 8 Mile Lake, north of the Alaska Range, the surface looked quiet. Dwarf shrubs, moss, lichens, a thin skin of summer life over ground that stayed frozen for most of the year. But the stillness was deceptive. Under that tundra sat permafrost, soil that had remained frozen for years, often centuries, and in some layers much longer. Across the Arctic, those frozen soils store about 900 petagrams of organic carbon. That is more carbon than most people can picture. At this site in interior Alaska, the active layer, the top band that thaws each summer, would soften just enough for roots, microbes, and water to move. Then winter would lock it down again. That seasonal rhythm had held the place together. By the late 20th century, researchers had started to worry that the rhythm was slipping. Air temperatures across the Arctic were rising faster than the global average. The concern was simple and brutal: if frozen ground thaws, dead plant matter that had been trapped in the cold could start decomposing. And once microbes wake up, they do not keep secrets. They breathe out carbon dioxide. In wetter pockets, they can also release methane. That was the fear hanging over Alaska's tundra. Not a dramatic collapse, not a crater opening in the earth, something slower, a buried transfer of ancient carbon from ground to sky. The problem was that no one could see it happening in real time. Permafrost does not announce itself. It softens by centimeters. The thaw line drops deeper in late summer. The moss dries. A patch of lichen disappears. A shrub grows slightly taller. To a satellite image, some of that can even look healthy, greener, more productive. Less like a dying ecosystem than a changing one. That is what made the Arctic so hard to read. A landscape can appear more alive while moving closer to instability. By the early 2000s, scientists working in Alaska were tracking exactly these contradictions. At places like Toolik Lake and the tundra near 8 Mile Lake, they were measuring plant growth, soil temperature, thaw depth, and the movement of carbon through the ground. What they kept running into was uncertainty. Some models suggested warming would trigger a fast carbon release. Other field results suggested plants might temporarily absorb enough carbon to offset part of the loss. So which story was true? Was the tundra becoming a source of greenhouse gases, or was it holding the line longer than expected? There was another problem. Most warming measurements focused on the air above the ground, not the frozen system below it. But in permafrost terrain, a 1-degree change at the surface does not stay at the surface. It moves down, into roots, into ice lenses, into dark soil packed with old organic matter, into a world that had been sealed off by cold. Then one detail started bothering the researchers. In some warmed plots, the deeper soil was not just thawing farther, it was staying vulnerable longer. By September, the thaw depth had increased by 10%. And that meant the most important layer in the story was no longer the one anyone could see. So the men studying this place made a decision that sounded almost reckless. If the Arctic was going to warm anyway, they would warm a piece of it first, not the whole tundra, not a giant landscape experiment visible from the air, just controlled plots at the Carbon in Permafrost experimental heating research site near 8 Mile Lake, where every centimeter could be measured and every change could be tracked. That was the logic. Disturb the ground on purpose. Watch what responds first. The obvious idea was to heat the air, but that was the first twist. Air alone was not the real target. The real target was the soil profile, the frozen system below the plants, below the moss, below the layer most people mistake for the Arctic itself. So the researchers designed two different kinds of warming. In summer, they used open top chambers, low clear structures that trapped heat close to the vegetation and raised midday air temperatures by about 1.0 degrees Celsius. In winter, they did something stranger. They built snow fences, not to keep snow out, to hold more of it in. That mattered because deep snow acts like insulation. It keeps brutal cold from penetrating the ground. Instead of exposing the tundra, the fences protected it from winter air, allowing the soil below to stay warmer. To most people, that would have sounded backward. More snow, warmer ground. That contradiction bothered people, including some of the researchers themselves. A few men in the field worried they were creating an artificial system too weird to trust. Others argued the opposite, that the setup was realistic precisely because Arctic winters were already changing, with shifting snowfall, altered wind patterns, and deeper drifts forming around expanding shrubs. The debate was not academic. If the warming method was wrong, then every result after it would be suspect, and there was risk on both sides. Do too little, and the tundra stays quiet long enough to tell you nothing. Do too much, and you stop simulating climate change and start manufacturing damage. That line was thin. At 8 Mile Lake, the winter treatment raised soil temperatures at depths between 5 and 40 centimeters by 2.3 degrees Celsius. That is not a dramatic number when you hear it once. In permafrost ground, it is enough to change timing, enough to change thaw depth, enough to wake processes that had spent years close to frozen, but not fully dead. And then came the unsettling detail. The experiment that was supposed to separate summer warming from winter warming began blurring the two. As shrubs responded, they trapped even more snow. The treatment started reinforcing itself. A small manipulation was already trying to become a system. That hit the team hard, because now the question was no longer whether the ground would respond. It was whether they had touched one lever and pulled 3 more with it. In the end, they went forward. Plots were marked, sensors were installed, snow fences stood across the tundra, the chambers were set in place. And beneath a landscape that still looked empty and still, the intervention finally began. At first, the changes looked almost encouraging, not dramatic, not catastrophic, just subtle signs that the warmed plots were becoming more productive than the untouched tundra beside them. Shrubs thickened, bud break came earlier, senescence arrived later. On paper, that meant a longer growing season. In the winter warmed plots, above-ground biomass increased by 20%. Net primary productivity rose with it. Canopy nitrogen mass also climbed by 20%. For a while, those numbers brought relief. Some of the men on the project thought the surface might be compensating. If plants were growing faster, maybe they could pull enough carbon from the atmosphere to balance what the soil was beginning to lose. That was the hopeful reading, and it was not foolish. In some long-term tundra observations, the carbon balance had not collapsed. At least, not yet. In certain places, new vegetation seemed to be holding pace with change, but the experiment at 8 Mile Lake was starting to split into 2 different stories, one above ground, one below it, and they did not agree. The first serious warning came from timing, not midsummer, when the tundra looked active and alive, not the bright season people instinctively focus on. The real tension appeared closer to the edges of the year, when soils hovered just below freezing and tiny temperature shifts mattered more than anyone wanted them to. That was the mini twist. The most dangerous warming was not always the warmest warming. It was the warming that arrived at the threshold. When researchers powered the heaters during the 2015 to 2016 field period, they saw a response almost immediately. Within hours, the warmed plots began releasing more carbon dioxide than the controls, not slightly more. Across the measurements, ecosystem respiration rose by nearly 50%. That number landed hard. Men who had spent years thinking in slow ecological trends were suddenly looking at a system that could answer in real time. The ground was not passive, it was reactive, and the deeper problem was becoming harder to ignore. The low plant cover in these plots meant respiration was closely tied to the soil itself. So when fluxes jumped, the question was no longer whether the Arctic surface looked greener. The question was what the microbes were doing underneath it, and underneath it, they were waking up. Cold had once kept decomposition slow. Now the insulation from deeper snow, the warmer soil, and the increased thaw depth were beginning to loosen that control. What had been stored in the ground as dead organic matter was becoming available again, not all at once. That is what made it worse. It was incremental, measured, easy to underestimate. Then came October 2015. One of the largest effects showed up not during the lush part of the season, but late, when most people would assume the tundra was shutting down. That shook the team, because if the shoulder season was this sensitive, then the Arctic was not simply warming. It was extending the window in which buried carbon could escape. And that meant the experiment had just exposed something far bigger than a heated patch of soil. What emerged was not a dead tundra. That would have been easier to understand. What emerged was a landscape that looked healthier at the exact moment it became more dangerous. Over time, the warmed plots grew greener and shrubbier. In the winter warm treatment, above-ground biomass rose by 20%. Canopy nitrogen rose by 20% too. From the surface, it looked like recovery. More leaves, more growth, more carbon being pulled out of the air. If you stopped there, the experiment would seem reassuring. That is what made the next result so unsettling, because the soil was telling a different story. At depths between 5 and 40 centimeters, winter warming had raised soil temperatures by 2.3 degrees Celsius. The growing season thaw depth increased by 10%. That extra thaw did not just change roots, it changed access. Microbes were reaching organic matter that colder ground had kept out of circulation. Carbon that had been protected by frozen conditions was being exposed to decomposition for longer parts of the year, and when the system was actively warmed, the response was immediate. Ecosystem respiration rose by nearly 50% compared with the control plots. That number hit like a warning siren. The plants were gaining, but the soil was spending faster. That is the contradiction that broke the simple story. A greener Arctic does not automatically mean a safer Arctic. In fact, the added plant growth may help hide the problem for a while. More shrubs catch more snow. More snow insulates the soil. Warmer winter soil deepens thaw. Deeper thaw exposes more buried carbon. The experiment had started as a manipulation. Now it looked like a feedback loop. That was the mini twist buried inside the payoff. The very signs many people would read as resilience, thicker shrubs, longer growing seasons, denser vegetation could also be helping the ground warm from below. The tundra was not choosing one direction. It was doing both at once, holding more life at the surface, losing more stability underneath. And this was not happening in some abstract computer model. It was happening in measured plots in Alaska, with sensors in the ground and changes tracked over multiple seasons and years. By the time long-term observations came in, the pattern was harder to dismiss. At some Arctic warming sites, researchers reported that experimentally warmed plots had become visibly greener over roughly 20 years. That visual transformation mattered, because to an outsider, greener often means healthier. Here, greener meant the system was rearranging itself, not toward balance, toward a new state no one could fully predict. That is why the experiment disturbed so many scientists. The logic they wanted was simple: warmer temperatures, more plant growth, partial compensation. The logic they found was layered: growth on top, loss below, and feedbacks linking both. A patch of tundra had exposed a climate trap, and if that trap could appear in a controlled plot near 8 Mile Lake, then the real question was no longer what happened in that experiment. It was how much of the Arctic was already behaving the same way. That possibility is why this experiment mattered far beyond one set of warmed plots in Alaska. 8 Mile Lake is not the Arctic. It is a sample, a controlled wound, a place where scientists could force the future to arrive early and watch which part of the system broke first. What they learned was unsettling. Permafrost does not need to collapse in a single dramatic event to become dangerous. It only has to thaw a little deeper, stay warm a little longer, give microbes a slightly wider window. That is enough to start moving ancient carbon back into the atmosphere, and the scale behind that risk is hard to ignore. Arctic soils overlying permafrost hold an estimated 900 petagrams of organic carbon. Climate models project 3.1 to 7 degrees Celsius of surface air warming over permafrost regions by 2100, with the top meter of soil expected to warm by 3.2 to 5.8 degrees Celsius under major emissions pathways. Those are not abstract numbers, they describe a system that is already close to a threshold. The mini twist is that the Arctic does not always advertise danger in the way people expect. It can look greener, richer, more biologically active. A valley can appear to be recovering while the ground beneath it is losing one of the conditions that kept it stable for thousands of years. That is what makes permafrost so difficult, even for experts. The warning sign is not always loss. Sometimes it is growth. That realization changed the way many researchers think about climate feedbacks. It is no longer enough to ask whether plants are growing faster. The harder question is whether deeper soils are waking up even faster than the vegetation above them can compensate. And in many places, that answer may depend on season, snow, moisture, and a few centimeters of thaw. A few centimeters. That is the scale at which a global problem can begin. There is still a reason these experiments matter. Not because they offer comfort, because they offer lead time. Field studies like this show where the hidden leverage points are snow cover, winter insulation, thaw depth, microbial activity, and the difference between a landscape that stores carbon and one that starts releasing it. That knowledge is not small. It gives governments better forecasts. It sharpens Earth system models. It tells northern communities, engineers, and land managers that what happens under the surface can no longer be treated as background. The Arctic is often described as remote, but there is nothing remote about a feedback that can accelerate warming for everyone else. In the end, that patch of heated soil did not break logic. It exposed a deeper logic people were not ready to face. A living surface can hide a failing foundation, and in the Arctic, the foundation is measured in frozen ground, buried carbon, and temperatures changing by just 2.3 degrees Celsius. If you want more stories where one small place reveals something much bigger, stay with this channel.